All right, so the hot mic today. All right, so I've got 405 up here, so I'm going to get started. Today is February the 26th. So we're going to we'll get to polymorphism today. As far as what's due, tutorial 6. To do tutorial 6, today's lecture probably come in handy just to make your print function virtual and to see how that is done. Not that it's a super difficult thing to do, but yeah. Other than that, tutorial 7, I just didn't get it out. It's ready, but I didn't get it out yet. Um, yeah, that's where we stand, I guess. Any questions? Okay. So, well, we're gonna do a short review. So last class we were talking about inheritance. Well, we'll do a short review, then we'll do the woo clap that we didn't get to last class. So some of the more prominent themes are, of course, member access, right? So access fires, and in that respect, it's really no different from composition, right? So if I have a base class that I inherit from, it's as if I have a base class member in terms of what I can access, except for this protected. That's a little special. That says, well, you can actually access that in your inheritance. But everything else is the same. If it's private to the base class object, then it's invisible to me. And if it's public, then it's perfectly visible. And that extends, however deep we want to go down the inheritance hierarchy. In terms of construction, the base class members are constructed first. That also follows from the idea that it's a lot like composition. So the contained object gets constructed first, or the base class gets constructed first in this case, followed by whatever's next going up the hierarchy or down, depending on how you want to look at it, followed by the actual class constructor of the thing we're trying to build. And then when we destroy things, they go in the opposite order. So the thing we wanted to build is destroyed first, and then the parent part of it, and then the whatever ancestor parts of it are ready. All right, and that's if there's a contained object. Seems pretty straightforward. Constructors are always called, and if I call a base class constructor from a derived class, we use the base class initializer syntax, which is a lot like member initializer syntax. In fact, so close you would think they were almost the same thing. And then that brought us to public and protected and private inheritance, which we lose this is a feature, right? So if this goose inherits privately from animal, then I don't have all of the animal behaviors because these become private. But we saw that we can actually solve problems and we can sort of promote these things to public if we want to. And then multiple inheritance, which there's a bunch of different types. So distinct base class, multiple inclusion of a base class, in this case person, or the diamond hierarchy. If we use virtual inheritance, then, student says, I want to virtually inherit from person. And if employee also says, I want to virtually inherit from person, then when the compiler puts it all together, they're going to say, well, I only need one instance of person up here. I don't need the multiple. And so that's where we left off. And we'll do a short quiz on that and then move on to polymorphism. All right. Incidentally, I don't know if this may not be like the heartbreaking news, but so for assignment 4, I am considering like abandoning the X11 stuff. Just to give you guys like a different view on the tools that you've been using, and sort of take some of the emphasis off of, just maddening technical details. But yeah, I don't know. If you guys have any feedback or thoughts on the matter, I'm happy to hear it. There's really not much left to do. I could make an assignment 4 based on it, right? We could do some design patterns and templates and operator overloading, and we could sort of flesh things out. But in terms of functionality, like once you get to inheritance, once you finish assignment 3, you're going to find it really add features. And so if it's something you wanted to show to an employer, you could definitely, you could show them what you got, or you could spruce it up a little bit and then show them that. Yeah. All right, let's see what, can't even remember what I asked you guys. So let's see what it is. A derived class can access all members of the base class. Oh, so we're gonna start easy, I guess. True, false, and none of the above. Is that it? What do some people? I guess true. Well, I guess it depends on what you mean by access. I guess directly. I suppose the wording is a bit ambiguous here because uh, you do not have direct access. As a derived class, if the base class has some private, I do have, I guess, indirect access. So, you know, depending on how you interpreted that phrase, true or false could both be correct, but the answer we were looking for was false, right? So a derived class cannot directly access all the members of the base class, only if they're protected or public. Where are we? So consider the two following, oops, stop that. Consider the following classes, 3 classes, I guess. What order are the constructors called in? And well, there's a little trick to that, right? I tried to trick you a little bit. Because there's no explicit constructors here, but each class does get a default constructor. So what order would those default constructors be called in? Gee, oh, geez, I don't even remember. What was it again? Well, so we made, I mean, I could have been more specific and said we're making a bird. That would have been a good idea. So let's assume we're making a bird. Then, bird contains an egg and it is a derived class of animal. So, well, the animal gets called first, right? So I have in some sense, yeah, I'm going to abuse the UML notation a little bit here, but bird, and then inside that bird is an egg. So we could think of bird and egg as one unit that inherits from animal. So the animal gets called first. And then when I have a container and a containee, the containee gets called first before the container. So it goes animal, egg, and then bird gets called last. So this is number 1, this is number 2, and this is number 3. And let's see. You guys, animal, egg, bird. So yeah, it's actually number 3. All right. Okay, I think this is, consider the following code. Would this run? Why or why not? And yeah, so the key to this one is, of course, this private keyword. So public inheritance is the inheritance that we all are used to. And in public inheritance, this would work. I mean, we did this example, although we haven't really taken base class handles to derived classes too much yet. There's no is-a relationship. That is correct. So number 2 would be right. Oops. There is no is-a relationship. So when I privately inherit from somebody, I lose the is-a relationship. I inherit all their members, but the thing that defines an object is the public functions. That's really, that's everything, because that's what you can call on a member of that class. All right, and then finally, here is our multiple inheritance example. Actually, this is the example that we looked at last in the previous class. So there's a base class called animal, and animal has a name. And then human and horse both virtually inherit from animal. And then the centaur inherits from both human and horse. So how many name members does a centaur have? And I mean, there's basically, well, I mean, I think 0 through 3, but there's basically 2 of them that we're really concerned with. A centaur inherits from a horse and a human. And horse and human both inherit from animal, but the question is, and I'm running out of space, let's call that animal and call this animal. So the inheritance hierarchy either looks like this, or it looks like this. So I either have 1 instance of animal up there or 2 instances of animal up there. So it is 1 or 2. Yeah, the virtual keyword means that the answer is actually 1. Right, so the virtual keyword gives us when I say virtually inherit, if horse says I want to virtually inherit from animal and human says I want to virtually inherit from animal, then what they're saying is that if you ever sort of combine us together, then we only need 1 instance of that animal part. So yeah. All right, so that's the woo clap. Any questions? Okay. All right, so that's inheritance, and that brings us to polymorphism, which is, yeah, we're good. Okay, so polymorphism. I think, well, polymorphism is like the crowning achievement of object-oriented code, but it's really just an instance of late binding. So we're going to talk about what is polymorphism, and then we're going to talk about all the technical details, how we do it in C++, and well, in C++, actually, of course, you have an option of whether or not you actually want to use polymorphism. And then we'll talk about abstract classes, and then we'll talk about, well, if you're not using polymorphism, you could try dynamic casting. It is more brittle, but sometimes it's the appropriate thing. And then later, this is actually not part of these slides, but I did sort of separate these topics, and I forgot to redo this table of contents, but these are closely related, right? Design patterns, and then behavior, what is it called? Behavior classes and the strategy design pattern, right? So that's an example of design patterns that use polymorphism to achieve their goal. But we'll get to that probably after. Okay, so what is polymorphism? Poly means many and morph means shape. And every time, so this is, every time I read this, I don't know, some of my references might be dated, but I'm sure, I know The Simpsons is still on. I don't know if anybody is familiar with the monorail episode. But if you are, then this will make sense. And if not, well, I don't know. Sorry, but yeah, the polymorphism basically means that I get different behavior, but in some sense, the same category of behavior from different objects using the same function call. And we'll talk about the technical details of that and also why it's useful. But an example is like if you've ever, I guess, made a game in like Pygame or something. And I mean, there are, of course, very complicated versions of games, but generally speaking, some games fall into the category of being quite simple in that you have just basically a game loop that says like, while running. And then some stuff happens, but the primary thing that happens is we have like some data structure full of game objects, and we call update on each of them. And that does most of the stuff for our game. So the game loop itself is very simple. It's just a very general algorithm, loop and update, and then maybe draw some stuff. But in these update calls, a whole bunch of details happen, right? So that in this case, so what does update do? Well, it depends on the type of the game object. So which derived class is it specifically? If it's the hero game object, then of course we're going to take inputs from the controller, and maybe we're going to center the camera on them and stuff. And if it's one of the bad people or whatever, then they're going to take their input from AI and maybe whatever. You get the idea. So these update calls it's the same function call, but a lot of different behavior inside those function calls. So yeah, polymorphism is a construct for making programming easier. Basically, at the most basic level, I call a function, but there's a bunch of them to choose from. Okay, so this is an abstraction layer. And the one nice thing it does is we can focus on algorithms, general algorithms, right? So a game loop is very general. Update everything, draw everything. Is the game over? No? Well, try it again. Yes, we call similar functions shared between related classes in this case. And then the nice thing about it is, well, not only is our core algorithm simple, but we can update it. We can add new objects. We can add new behavior. We don't have to change the core algorithm. So polymorphism often comes up with design patterns. Design patterns are ways to sort of tackle problems, and generally they tackle them by sort of decoupling them, which we'll talk about. So what happens is we create a generalized interface, and then we'll see. How you implement polymorphism depends on the languages, but in general, we have what's called a generalized handle. We talk about handles later, but a handle is basically any variable that can reference, I think I have handle. I should move this. It's an identifier used to access an object, right? So the variable itself can be a handle, a reference to a variable can be a handle, or a pointer to a variable can be a handle. It's just a way I have of accessing some object. And then, so we're going to use a generalized handle, like let's say an animal, and then we're going to call on a specific implementation. So I'm going to say like animals speak, and my chicken will cluck, and my dog will bark, and stuff like that. So in C++, to use polymorphism, we need inheritance. I have a base class handle, and that refers to some derived class functionality. And yeah, so the classic example, well, generally speaking, we should implement the same category of behavior. It sort of makes sense, but in a specialized manner. So, animals can speak, but cats speak by saying meow, and dogs speak by saying woof. And really, polymorphism is an example of late binding or dynamic binding. So this idea is not strictly associated with object-oriented programming and polymorphism, right? It's just basically, at a certain point, I have a function call, and then I figure out at runtime which function to call. right? It's called, used to be called late binding, and then polymorphism sort of took over from there. But yeah, it keeps the behavior of our program is dynamic without having to make like massive changes to it. Yeah, some of my slides I think I have to clean up. I think I repeat myself quite a bit. But one of the things is that we maintain this layer of encapsulation. So a client class would be the one that's taking the base class handle and calling some function. That client class does not need to know what the actual underlying object is or what the function call is going to be, right? Specifically, right? It knows the name of the function, but it doesn't know which specific function it's going to be using. So we maintain that encapsulation. If you have to use casting, that's not polymorphism, right? The casting is kind of brittle, and we'll show you examples of it, although it does have its place. All right, so yeah, we've seen most of this. Yeah, I think I really do repeat myself. So generally, in terms of implementation, how does this work? Well, what happens is that I take my animal pointer and I say like speak, and it goes to the animal object, and there's what's called a vtable pointer. So I jump to the object, and then I jump to the table, and then that table has a list of all of the functions for that specific object and where they are, right? And so the reason why each of these has a table is because when I'm using inheritance, right, I might have a dog that's part of a whole hierarchy of things, or I might have a dog that's just a dog, right? I could have a Cocker Spaniel or you know, a dog named Lassie, but or I could just have a general dog. All right, core algorithm stays the same, blah blah blah. Yeah, so in C++, we use inheritance. We can have inheritance without polymorphism, as you'll see. The first example we'll see is inheritance with no polymorphism. So the default behavior in C++ is not to do this fancy switch at runtime thing. The default is just to kind of do the obvious thing. So yeah, let's take a look at an example. I was just like, how many times can I say polymorphism in 10 minutes? So we have, let's just briefly go over what sort of inheritance hierarchy we're looking at now. So very simply, I'm not going to put a lot of detail into these UML, but I have an animal base class, and then I have a bird that inherits from the animal, and then I have a chicken that inherits from the bird. Right, so a chicken is a bird and a bird is an animal. And then I also have inheriting from animal a cat. And maybe we'll add some more animals as we go, but this is what we're going to start with, just to give you an idea. So we start out, this is our animal base class. And of course, we have the function speak. Name is protected, so we can access it in our derived classes. So the cat speaks by saying meow, and we do have code here. Animal does speak, but we don't really know what an animal says, so we just sort of generally say that they speak. But my bird, well, tweets, right? But then unless it's a chicken, if my bird is a chicken, then the chicken's going to cluck. And I call the base class constructor because I don't, well, I guess I do, but just to initialize everything. So I make an animal, a Tweety bird, a chicken, and a cat. And then we have the barnyard harmony. They all sing in time. Yeah. Okay, so barnyard harmony, the animal owl, we don't know what kind of animal, but they speaks. The Tweety bird tweets, little red hen clucks. The cat meows. So everything looks good so far. But let's try something a little bit different. So since a chicken is an instance of an animal, I'm going to make an animal pointer. And then I'm going to point that animal pointer at the little red hen, right? So pointer takes a memory address, and this is the address of the red hen. And then through that pointer, I'm going to ask the chicken to speak. And in this case, up here, the chicken clucks. When I ask it to speak through the animal pointer, it just says speaks, just like Al the animal did. Right, so this is by default, C++ kind of does just the dumbest, or not the dumbest thing, but the most obvious thing, which is that, oh, I have an animal pointer, you must be asking me to speak like an animal. So if you say animal pointer speak, I go all the way up here and run this code, right? I don't even check what kind of animal you're actually pointing at. I just assume that it's an animal. Okay, and all right. To prove that that is not just a thing that pointers do, I'm going to make a chicken pointer now and point that chicken pointer at the little red hen. Now I have a chicken pointer pointing to a chicken, so that, you know, makes sense. And then I'm going to ask the little red hen to speak again. And in this case, the little red hen clucks like a chicken, right? So again, the compiler just looks at, well, this is a chicken pointer, so I'm going to jump to the chicken speak function. And just to finish off our little tour, I'm going to make a bird pointer, the little red hen, the address of, and then I'm going to have the bird pointer speak. Right, so the bird pointer is still pointing to the little red hen, but now the little red hen is tweeting like a bird. Right, so all of that is based on this this pointer, and it's not. Yeah, all right. Let's just complete the. I'm going to do the same thing with the Tweety bird. I have a bird pointer. I pointed at the Tweety bird. I'm going to ask the bird to speak. Just, we know what's going to happen, but let's just make sure. I mean, there's one thing to know what's going to happen, and it's another thing to run it and then get it wrong and then be embarrassed in front of everybody. But, and then we're going to make an animal reference, right? So if you remember references, they're kind of like pointers, but they're like an alias. And I can take an animal reference and assign it to the Tweety bird and then ask the Tweety bird to speak. So bird pointing to a bird, the bird tweets. That's not unexpected. The animal reference points to the derived class bird, and then the bird just speaks like an animal. So reference or pointer, we get the same behavior. This stuff we don't really need. Questions? Yeah. Yes. Yeah. So we're going to get to that. So it's Java does things. Yeah, we'll talk about that. We'll get to that. Yes. So abstract classes we can make, and we are going to make. First, we're going to make a virtual class. All right. Okay. So by default, C++ just does the obvious thing. You give me a chicken handle and you ask it to speak, I'm going to cluck. If you give me an animal and you ask it to speak, I'm going to speak like an animal. So yeah, if I have a base class pointer pointing to a base class object, I get base class behavior. If I have a derived class pointer pointing to a base class object, well, that's actually not allowed, right? We can't have a chicken pointer pointing to an animal because although a chicken is an animal is not necessarily a chicken. Base class pointing to a derived class pointer, well, I still get the base class behavior. And derived to derived, I get the derived class behavior. And this is what's known as static binding. So what that means is that at compile time, the compiler knows which function it's going to call, right? Because it can see the handle type. So that's not really what we want. So let's tell the compiler to turn on dynamic binding. And dynamic binding is what you're probably used to with Java, where I have, you know, if I'm pointing to some sort of derived class, it looks for the correct function. And to turn it on is quite simple. So we saw virtual inheritance. So we use the virtual keyword. We're going to make a virtual function. And I'm going to add it to the base class. Well, we'll just add it to the base class. Yeah, okay. For now. So virtual speak and then make, and then, okay, so I have an animal base class pointer pointing to the chicken object, and look at that. Now little red hen clucks. I have this is a chicken pointer pointing to a chicken. I have a bird pointer pointing at the chicken, and again, I still get the chicken behavior. I don't get the little red hen tweeting. This is a bird to bird, and this is the reference, an animal reference pointing to a bird, and I get the bird behavior. So now I get what's called dynamic binding, where at runtime, the compiler or the runtime system, well, it just does a table lookup, right? So it goes to the vtable, and then based on the vtable, it goes to the vtable pointer, and then, I'll show you in a second. I'll show you a couple other things though. So I only need to add this to the base class, and then this is inherited all the way through the class hierarchy. I didn't really show you cat, but if I did show you cat, you would see that it also gets this dynamic binding. However, because we are, considerate programmers, it's considered good practice to add it to all of the derived classes. And that's, in some sense, self-documenting code, right? So if I see the virtual keyword here, I know that, hey, maybe I should check my animal base class to see what's going on there, right? And then I know, oh, this is a virtual function. What was the thing? Jesus. Right off the top of my head and gone. Where'd it go? Well, let's just verify that that works the same. Yeah, so animal pointing to a chicken, we get the chicken clucking. This is chicken pointing to chicken. That's completely expected. A bird pointer pointing to a chicken still clucks, right? So we add the virtual keyword all the way down, just to be considerate. I think I have, if I'm not mistaken. So I have an animal. This is just a little test class. An animal class, and then a chicken inherits from animal, and it's got an egg and whatever. But it has a virtual print function, and if you look at using this little tool, the actual layout, well, this is my chicken class, and it contains a instance of the animal base class, but the new thing that's added is this vtable pointer because of the virtual keyword. So now if I have an animal pointer, it jumps to this vtable pointer, and this vtable pointer points to a table. And I go to the table, and it says, well, for this thing, it gives me the address of the chicken print function, right? Because this is a chicken in some sense. Well, in every sense, I guess. Whereas if I have an animal, I still have the vtable pointer, but this jumps to a different table, and then the address of the print function is the animal print function, right? So it's just, and now this is the sort of most popular way to do it. A compiler is free to implement this however they like, right? They don't have to do this, but this is sort of the most sensible way, I guess. All right, so yeah. So when we call a function on a class, there are two types of function calls. We use binding, which happens at compile time, which means that, well, that's just the default. We look at the handle type, based on the handle type, we jump to that function. Or we can turn on dynamic binding using the virtual keyword, in which case, basically, we're going to jump to the proper function, but we're going to take a little detour. We'll have to go look it up in a table. It takes a slightly longer, but it's not too bad. Oh yeah, I showed it here as well. So here I have a boat, and a sailboat that is a boat, and my sailboat and my boat. My boat looks like this. I have a capacity, and my sailboat sort of contains this boat. Base class, if I make this virtual, then vtable pointer is added to both of them. So it's my classes are now like 8 bytes bigger in this case. All right. So yeah, static binding. Again, I think my slides repeat an awful lot of stuff unnecessarily. All right, so what is a virtual function? A function that is selected for execution at runtime. So in Java, all functions are virtual, right? If you have a base class and it's pointing to a derived class, then it's going to call the derived class function. But in C++, we turn that on or off for each individual function, right? So we can figure out exactly how we want these hierarchies to be used. A lookup table is based on the object type, not the handle type. The virtualness is inherited all the way down the hierarchy. We just have to have it in the base class, but by convention, we include it in all the derived classes to document our code better. All right, so what does this mean for destructors? Because a destructor is just a function, and we don't call it explicitly. Well, we don't. You can. There's reasons to do that if you're using like an allocator or something, but we're not taking allocators, so it gets called implicitly for us. But what happens if we, well, let's take a look at an example actually. All right, so I have the same hierarchy. I have an egg now as well because our chickens are going to lay eggs. I guess our bird could lay an egg too, but so I have an animal class. I've included the destructor here. It doesn't do anything special, but it does announce that we're in the animal destructor. Here we're in the bird destructor. Here we're in the chicken destructor. What actually does do something, it deletes the egg, and in the constructor, it makes a new egg. So we're using dynamic memory here, so it's rather important that we get the destructor called. And then we have a cat. Well, the cat doesn't do much, but we're going to take all of these. We're going to dynamically allocate a bunch of these animals and store them in pointers, and then we're going to push them onto a vector of pointers. So I'm not sure how, well, let's talk a little bit about what vectors are specifically. You've built things that are very similar to vectors, but so I have my, well, let's say I have a stack frame that I've declared a vector in, and then what the vector is doing is, not initially, but once I start adding stuff to this vector, it's gonna allocate an array on the heap, right? So this is my stack, this is my heap, and there's what's called the backing array, which you guys should be pretty familiar with. On the heap. And then each of these is a pointer, in this case, to an animal. And so when I add an animal, let's say I make a new animal, right? Al the animal. And then I push it onto the vector. Well, I'm pushing the animal pointer onto the vector, so it's going to point to Al. And you made data structures that look a lot like this. Now, Tweety Bird and etc. Now the vector does something a little more than our data structures did. It will actually grow the backing array as needed, right? So I'll technically never run out of space unless I run out of heap space, which is very unusual. But so we don't ever have to worry about like having too many things in our vector. I say grow and not shrink because I'm pretty sure it does not shrink ever. Even though it could, that's kind of wasteful. Statistically, if you store a million things in a vector, you'll probably store a million things in the vector at some point in the future. So, all right, so that's what our vector does. And we'll talk a little bit more about vectors moving forward. We're going to try and sort of flesh out, because Well, because we're rolling our own data structures, but they're very simple, and typically you wouldn't do that, right? It's very good to learn how these things are formed, but in the real world, if you need a data structure, you're going to use the vector from the standard template library, most likely. And if you don't need a vector, maybe you need a list. Well, there's a list there too. So I'm going to push these things back, and then we're going to have the barnyard harmony. And we'll get to the barnyard slaughter in a minute. The other thing about vector is this at function. Here, let's first do the barnyard harmony. So barnyard harmony, owl speaks, the Tweety bird tweets, little red hen says cluck cluck, and the cat says meow. We haven't deleted anything yet because I'll save that for later, but we use the at function here. We said at I, and that, when we did that, of course, if this is location I, when I say at I get back this pointer, right? So some memory address, and then I can follow that pointer and call like speak on it. But we've seen vector before, actually, and we've seen something a little bit different that does the same thing, the subscript operator, right? Which actually is just a function call. I think if I hover over it, you can see this is what the function looks like. So when I write the function, it looks like this, and then when I ask for the function to be executed, it looks like this, right? So this is operator overloading. And barnyard harmony looks exactly the same, all right? But there is a difference. So anybody know the difference? Or anybody guess the difference? Okay, so here, well, let's try something. Let's try this. Or let's make it obvious. Let's say our finger slipped, we wrote 40 there. I think I did something like that on your assignment test code. Barnyard harmony, I get a seg fault right away. Okay, I get a seg fault because this is like way outside of bounds. If I had actually, let's just try this for fun. Let's pop the last thing off the back. Now there's 3 things on the vector. I wonder if that'll work. Yeah. C++ for you, right? So technically 3 is not accessible. This is not technically a valid location in my vector, but it does actually still contain the memory address for the cat, which I popped off the back here. So yeah, this is what's called undefined behavior, which means in C++, I've accessed this memory I shouldn't, but it still worked. Let's change that to at 3. And here, we get an exception thrown. Okay, so at actually does bounds checking. So this, and if we're out of bounds, it's going to throw an exception, which is safe. It takes a little bit longer to do the bounds checking, right? Not very long. It's just like one comparison, but it's not nothing either. This is essentially exactly as safe as doing the same thing to an array is, right? So this basically forwards the call to the array, and whatever happens, happens. So that's the difference. Questions? Okay, so let's back. I should be fine. All right, let's kill all our animals. So we're going to, I have specifically pointers pointing to these animals. They're the animal pointer is pointing to an animal owl, the bird pointer is pointing to a bird, chicken pointer is pointing to a chicken, and a cat pointer is pointing to a cat. So when I call delete on all of these, I'm getting the correct type for each of those. So after the barnyard harmony, the barnyard slaughter, well, Al, the animal, is destroyed, right? This destructor is called. For my Tweety bird is made up of a bird part and an animal part, and they're both destroyed. That's good. Chicken is made up of a chicken and a bird part and an animal part, and all three are destroyed. That's wonderful. And then the cat also, and I can run it with Valgrind. And I have no memory leaks. Even though I had some dynamic memory in the chicken, everything's handled. Okay. This is kind of awkward though. So let's get rid of that. And well, why don't we just loop over the vector and call delete on each of these elements in the vector. Makes more sense. Whoops, I shouldn't have done that. Can I get that back? Let's back up just a second. I wanted to compare and contrast here. E3 and then E3. Okay, so here everything is destroyed correctly. When I get down here to my barnyard slaughter, well, Al is destroyed, but Tweety bird, only the animal part is destroyed. Little red hen, same thing, only the animal part, and Lily also, right? Because when I call delete on this, there's an implicit call to the destructor, but it uses static binding, right? Because this is a static function. It's just a function after all, and it's static. And if we run that with Valgrind, of course, we have a problem that the egg did not get deleted because the chicken destructor did not get called. Okay, so well, we know the solution, or at least, we can make a reasonably educated guess at the solution is that let's make that virtual. And then, like good programmers, let's make all the rest virtual. The cat. This part is not necessary, but just to be nice. And now let's try our barnyard slaughter again. And here we can see, we got everything is destroyed. So now we have this, we have the correct implementation. We have dynamic binding on our destructor, which means that when I call delete on this animal handle, if it's a chicken, it's going to jump to the V table and look up the destructors and then call each of them. Okay. And if we check that with Valgrind, yes, no memory leaks. All right, questions? Okay, so there is a bug that I cannot reproduce, and now that I'm thinking about it, it might be because basically I use terrible packaging here, right? Very bad packaging, which basically means I'm putting all my implementations in my headers. Not only that, I'm putting all my classes in the same file. So maybe we get some advantage there, but let's say that I did something like this. Now this is going to be fine, but let's say that animal. I have an animal destructor that's virtual, but I don't have a bird destructor or a cat destructor. It's fine, right? I'm not specifically calling the cat destructor, but it's getting deleted. So no memory leaks, it works. If you try that in your assignment 3, I think you will get a crash. At least I get a crash when I do that. And I don't quite understand why it crashes, but I do know that if you want to save yourself some headaches, in every one of your classes, put a virtual destructor. And if it's empty, it's empty. That's fine. Even if it's empty, it has to be there. So you would just do this and then have, right? Just do that. If you have nothing to delete in there, still put it in, because I think otherwise, I don't know, I'll have to track it down. I've looked at stuff flow and stuff, but I have not found an explanation that I'm happy with. But yes, you will save yourself some headaches. And at the very least, it's not going to hurt anything. So I would highly recommend to do that for all of your classes. All right, questions? All right. Abstract classes. So yeah, if I have a non-virtual destructor, it calls the destructor based on the handle type. Even though I don't call it explicitly, implicitly, that's what's happening. It can result in unpredictable behavior, right? If you're using polymorphism at all of your destructors should be virtual, right? So, and yeah, probably you want to include them all, although I've not tracked down that bug yet, but so yeah, well, we've already done this top part of the table, but at the bottom part, if we have virtual functions and we have a base class pointer pointing to a base class object, we get the base class behavior. If we have a derived class pointer pointing to a base class object, well, actually, you're not allowed to do that. Derived class pointer pointing to a derived class object, we get the derived class behavior. And base class pointing to derived class, we get polymorphism. All right. So yeah, this is the special case where I have this base class pointing to derived class. All right, so that brings us to abstract classes. So an abstract class is a class that has at least one pure virtual function or an abstract function. So abstract is we have a function declaration, but no implementation. In UML diagrams, of course, you use italics. Let's just jump into the, well, the syntax for a pure virtual function is this, right? So I use the virtual keyword still. In my class header, I put equals 0. So if you know what one of these, right? So we call functions all the time, but what this actually is a pointer to a function. Right? This contains a memory address. So when I call print, basically when I jump to this memory address and start executing the code that you find there. So when I put equals 0, what I'm saying is that, well, there's no valid memory address for this, right? So if somebody calls this, well, actually, it won't even compile because it doesn't have a valid memory address. So if we do this, right, so I'm using bad style, so we're doing everything in our header, but generally you would separate your header from your CC file or your source file. So if we do this, then we do not put an implementation in the source file. And if our class has at least one pure virtual function, it's an abstract class. And any derived class must override this function, or else we also are abstract by inheritance. Okay. So we have our same inheritance hierarchy: animal, bird, chicken, cat. They're going to do the same old barnyard harmony, then a barnyard slaughter. And we will do that first and then come back and break it all or whatever. So barnyard harmony works great. We're using dynamic binding or polymorphism, so everybody's doing the thing they should. Everything's destroyed correctly. Let's say we want to add some functionality to our animal now. We don't just want a song, we also want a dance. But when it comes to the animal class, well, the animal class is too general. I don't know how to make an animal dance. I'm just going to say, make that a pure virtual function. Okay, so that means no implementation, right? So these have an implementation that should be in the CC file, but if I had a CC file, I would not mention this one at all. And you can see that, well, our compiler is not happy with us. So object of abstract class animal is not allowed, right? So animal, there is no dance function, so it can't be instantiated. Bird, same thing. By inheritance, I inherit that abstract function. So now bird, I cannot make an instance of bird. And of course, chicken and cat have the same problem, right? Chicken now inherits it from bird, and cat inherits it from animal. Okay. We can still declare pointers, but we cannot instantiate any objects. So let's start fixing that, starting with our bird. Bird is going to dance, the bird dance. Dances the bird dance. All right, so now we have an implementation. Let's see, it looks like our compiler is already starting to lighten up on us. Yeah, so now bird is fine because we have a dance function. So it has a concrete implementation for every function. So we can make a concrete instance of a bird. And chicken, of course, inherits that dance function from bird. So chicken also we can make a concrete instance of. Cat still does not have a dance function, a concrete version, and neither does animal. So let's fix it for cat. Actually, let's fix it for chicken as well. Even though chicken inherits it, we can override it. Does the chicken dance? Now, one of these is a real dance. The chicken dance or the bird dance? Okay, I can't remember. If you're like 1,000 years old like I am, then once upon a time, people actually danced for entertainment because there was no internet. And one of these was an actual thing. It was called line dancing. It looks ridiculous, but yeah, it's a thing. All right, so now we have a chicken, we have a bird, and our cat. Well, I don't know. I've never seen a cat dance, but I've definitely seen a cat maul a small animal. So the cat pounces. All right, so we have concrete implementations for a bird, chicken, and cat. Animal, still no good. We cannot, that is an abstract class. We cannot make an instance of it. So let's remove Al from the barnyard harmony. And then, yeah, let's run it. Oh, I mean, we should call our dance function as well. So we've pushed all of these pointers onto our vector. And when we did that, of course, I copied the memory address from Tweety to the vector, but here the type was bird and here the type is animal. So I am using polymorphism. Barnyard dance. Okay, so yeah, the barnyard harmony works fine. The barnyard dance also works fine. The barnyard slaughter works great. So yeah, the only thing we can't do is make an instance of an animal. All right, questions? Okay. So as mentioned, so now we have like this polymorphic class. We have a very abstract base class handle that just says, you know, it speaks, but probably like that's kind of ridiculous. Let's make that virtual as well. So we have just an abstract animal that says like animals can speak and dance, but I don't know how they do it. You know, you figure it out when you make a subclass. Yeah, so we do. And now we have a very general algorithm, right? Sort of like the game objects describing before, we have a data structure, in this case, a vector of animal pointers. And then we just run loops on them and call different behaviors. So here we're going to all speak or sing or whatever. And here we dance. And then here we get slaughtered. So this is an example of like writing a general algorithm and then having specific behaviors manifest at runtime. And the nice thing is, if I want to add behavior to this, I can just add a new subclass. So in this case, instead of a cat, we're going to make a pig. And so the pig says meow. Well, no, not any pigs that I know. Rolls in the mud, right? So voila. So now I have a new class of animal with its own behavior, and I can say, well, make a new pig called Al, right? I didn't know what Al was before, but now I've gone back to school. I've learned that Al is actually a pig. So now I have an instance of a pig that I can add to my barnyard harmony. Now I had to, make a change here to like instantiate it, but none of these have to change whatsoever, right? These are nice general algorithms. And now when I run my code, I have a nice new behavior. I have a pig that says oink, and one that rolls in the mud, and also, it's eaten. So yeah, this is sort of the use case of polymorphism. Now I get to write these general algorithms, and the behaviors are defined in the subclasses. All right, questions? No, all right. So yes, if a class has at least one pure virtual function, it becomes an abstract class. And any derived class must override it or else become abstract. Let's take a look at, well, just a common pitfall, I guess. Or I don't know if it's common or uncommon, but so we have our animals. We have the copy constructor for animal. So we're just going to sort of mention when this thing gets copied. We have the destructor and we have the speak. So we're going to have our barnyard harmony the same as before. No barnyard dance today, but oh, we mentioned the copy constructor here. That's probably not necessary. So yes, make our animals, put them on the vector, and then have our barnyard harmony, and then we will try and break it. So we see our animals being constructed, pushed onto the vector. We have barnyard harmony, and then I didn't bother deleting them yet. Actually, I didn't bother deleting them at all. We're not going to bother. What we're going to do now is we're going to make a vector of animal objects. So the difference here is, of course, in syntax, I have animal here and I have animal star here. So what does that mean in a practical sense? Well, this was my vector before. I was pointing to a backing array on the heap that has animal pointers, and those animal pointers point to animals. But now, not right away, of course, but when I start adding things to this, I'm going to have an array of objects, just like we did in assignment 1. And then if I have my animal Al, and let's say Al's on the stack, and then I'm going to push Al onto this vector, well, what happens is Al's going to get copied onto the vector. And then if I have a Tweety bird, and I push Tweety bird onto the stack, well, Tweety bird will get copied onto the, sorry, not the vector, onto the vector, but also onto the backing array, right? So we have an array of objects, just like assignment 1. And so let's see what happens. So we're going to do a couple things. I'm going to push them all onto the vector. So these are just animal objects now. I'm going to push them onto the vector from the stack. And then I'm going to do the barnyard harmony. But let's push them onto the stack first. Or push them onto the, so here, I'm pushing animal onto the vector. I make a copy of Al the animal. That's to be expected, right? Pushing bird onto the vector. Well, I make a copy of Tweety bird, but I also make a second copy of Al. And then when I push the chicken, well, what's happening here? So how a vector actually behaves is following. When it's empty, there's nothing on the heap. It has a pointer that's pointing to nothing. And then I say, so I have a chicken, a Tweety bird, and an animal. I say add al to this vector, and it goes in and it makes a backing array of size 1, and it copies al onto that backing array. So we see the copy constructor being called. Then when I add Tweety bird, well, it's the vector says, well, my backing array is not big enough for Tweety bird, so I'm going to double the size of it. And it's not going to double it explicitly. It's going to make a new backing array. It's going to copy al, and it's going to copy Tweety bird from here. So it's going to copy al from here, Tweety bird from there, and if we had the destructors declaring themselves, we would see al get destroyed there. But I didn't want to clutter it too much. So that's our new backing array. It holds al and Tweety bird. Now when I try to add the chicken, it says, oh, again, I'm out of space. So again, I'm going to make a new backing array. I'm going to double the size. And then I'm going to copy al and the Tweety bird over. And then I'm going to add the chicken by copying the chicken over. And delete that. And then we have a cat. And we finally add the cat. But when we add the cat, of course, there is space for a cat. So we're going to add the cat here. And we can see that exact behavior when we look at what happens. So al gets copied first. We add Tweety bird. We have to double the size of the vector. So then we copy al, and we also copy Tweety bird. And then we double the vector again, and then we have to copy all 3 to the new vector. Well, we have to copy basically al and Tweety, and then we copy little red hen from the stack. And then when we copy the cat onto the vector, we have enough space. So we only copy the cat. Right? So the vector, the default behavior, runs out of space. It doubles in size each time. So that, and that works great. If you're using objects, though, you're calling the constructors and the destructors a lot, which can be wasteful. So something to keep in mind moving forward. We will come back to this idea again. But essentially now I have a vector full of objects, and now I'm going to do my barnyard harmony again. And so my barnyard harmony now is animal owl speaks, animal Tweety bird speaks, animal red hen speaks, animal Lily the cat speaks. So they're all behaving like animals now. I have virtual functions and everything, but yeah, what's the deal? What happened? Let's think about this. Essentially, a vector has a backing array. So let's just think about what this backing array is. It's a backing array of animals. And if I look at, say, my Tweety bird, so this is the bird. This is the memory that the bird is stored in. And inside the bird, there's an animal part, exactly like composition, right? And that animal part has the name variable. And then our bird doesn't have any member variables, but let's say it did. It had an egg or something. So when I copy bird, Tweety bird, onto my backing array, there's no room for the bird stuff, right? These are only animals. So I can only store the animal parts, which means that only this thing here of my Tweety bird gets copied into my backing array. And I lose the bird part. And so now this is an actual animal. I made a copy of my bird, but I copied it only the animal parts. And so when I call a function on this, it has no idea that it used to be a bird. It just sees an animal. So even if I had a pointer pointing to this, I would still get just the animal behavior. All right, so if you're using polymorphism, certainly you do not want to do this because you're sort of defeating the entire purpose of the thing. have to store pointers to your objects, not the objects themselves, because that will not work. Right, questions? Okay, so yeah, we're going to, again, as mentioned, we're going to keep coming back to this idea of the vector, and over time, we will sort of address all of these little things. Okay, so that is everything you ever wanted to know about polymorphism, and that is essentially what you're doing on your assignment 3, right? You're making components, arrays, you have a base class of components, and then the different types of components draw themselves differently. Some of them draw themselves by drawing a bunch of other things. Others, you know, write some text or whatever. So there is another way to, of course, figure out what the thing I'm dealing with is, and that's just to inquire. So what's the underlying object type? Well, we have this thing in C++ called the runtime type information, and don't know a lot about it. Well, I have looked all this stuff up before, but I've never used it because I forgot it as I looked it up. But there is like a type ID and a type info object, so you can get like strings for the class name and things like that. So you can query like, is this an instance of blah? Or you can use what's called dynamic casting. So yeah, let's see an example of that. All right, so we have our animal base class. It is an abstract class, pure virtual functions. And we have our barnyard animals, right? A bird, a chicken, a cat, and a pig in this case. And now we have our vector of animals. And we have our barnyard harmony where they're all going to sing, and then a barnyard dance where they're all going to dance. And then they're all going to be eaten. Okay, so the barnyard harmony, that goes swell. Pig says oink. Pig rolls in the mud. Dance, great. Let's say, though, that during the barnyard dance, I want to be aware of when the cat's going to dance because I saw a lot of mice in the field and, well, the cat's going to freak out. So we want to check when the cat is going to be dancing. And so we're going to use what's called dynamic casting. We're going to say, well, I'm going to make a cat pointer, and I'm going to say, like, well, see if you can make a cat out of this thing. So dynamic cast, it is a template. So I need to tell it what the type I'm trying to cast to is. And then I'm going to pass in a pointer, barnyard. Okay, so dynamic cast and static cast is something different. We'll talk about that in a second. But this will try to cast, so this is barnyard is a vector of animal pointers. So it's going to try and cast this animal pointer into a cat pointer. And it's going to be able to do that if it's pointing to a cat, right? So, and then we'll say if cat is not equal to null pointer. So if it fails, it's going to return a null pointer. But if it doesn't return a null pointer, then I have a cat, and I could say, well, what can I say? The cat sees a mouse and meows. And then I can say cat speak. All right. So now I'm, again, like I'm trying to introduce new behavior here, but instead of like making a subclass and using polymorphism, I'm just peering directly into these objects to see if they see what they are. Okay, so the barnyard dance, Tweety bird flies, does not see any mice. The little red hen does a chicken dance. The cat pounces and sees a mouse and then says meow. So yes, we did successfully find the cat and introduce new behavior based on what we saw there. And then the pig rolls in the mud. And then everybody gets deleted. So that's fine. And I'm going to show you how it's brittle in this case, but it's not like this is never used. Like this is definitely used. And if you used Java and you used, I don't know about Java FX so much, but I know like Swing, of course, when you you press a button, it triggers an action event, and then out of that action event, you try and cast whatever the thing is to a button. Say, is this a button? And if it is, then great, you call whatever function you're supposed to do. So they do this successfully in like, very professional libraries. But let's say this cat sees a mouse. What is it? Let's make it. It's going to be an instance of a cat. What is it? I don't know. A vegan cat. So the vegan cat does not care about the mice. All right. So a vegan cat would not chase a mouse, right? Because it's, vegan. I don't know. Percy? Sure. Okay, and then we're going to add our vegan cat to the algorithm. vcat. All right, and then nothing else has to change. So when I run this now, what happened? The vegan cat didn't do anything for some reason. Oh, I did not save it. All right. Okay, so the cat sees a mouse and meows, and then my vegan cat sees a mouse and meows, but this is behavior that a vegan cat, wouldn't care about seeing the mouse. So now it became brittle, right? If I subclass my cat, now all subclasses of cat have this additional behavior, and it may not apply to all of them, right? So there is a place for this, for dynamic casting and whatnot, but do be careful because you can break stuff. It becomes brittle now, whereas polymorphism is actually not brittle. It's very flexible and stuff. All right. So dynamic cast, the nice thing about it is that there is a static cast. Dynamic cast, though, will you do it if you don't know what the underlying type is, right? So this can fail a dynamic cast, and if it fails, it returns a null pointer. If I use a static cast is only when I know what this is supposed to be, right? So if we use a static cast, then it thinks everything is a cat because I'm saying like, hey, I know this is a cat. So just give me back a cat pointer. I don't care what you think it is. So in this case, that kind of backfires, right? So dynamic cast is for when we don't know. Static cast is like, I have to pass in a void pointer or something, but I know what the type is, and I can just, I can skip the part where it checks for everything. All right. Questions? Okay. So that's it for today. I guess next class we will start with the woo clap again. I believe that takes us to the end of almost to the end of polymorphism. We're going to do an example next week where we refactor. All right. So that's it for today. Have a good weekend and see you next week.